So our speaker for today is Kishore Patra. Kishore is a graduate student in the Berkeley Astronomy Department, working with Alex Filipenko on supernova polarization. Kishore graduated with a Bachelor in Science and Physics from the Massachusetts Institute of Technology in 2008. At MIT, Kishore did research searching for exoplanets that spiral into their host stars. Kishore grew up on the east coast of India before moving to the UK at 16 to study for the International Baccalaureate Diploma. In his free time, Kishore likes to watch cricket and badminton, take photo walks, and write stories. If you'd like to ask any questions relating to non-science things that Kishore does, you can also ask that in the chat, and he can address them at the end of the talk. So yeah, you can take it away, Kishore, and hope everybody enjoys the talk.
Well, thank you very much, Stephen, for that kind introduction. And thank you, everyone, for being here today. I know there's a lot of things going on in the world, but I guess it's a good time to step back and look at things outside our world for once in a while. So today I'm going to talk about exploding stars. And when I was a kid, growing up in India, I used to have a lot of questions about stars. I used to ask, like, what are they? Where do they come from? And why don't they fall back onto the earth? And generally what I got from other people around me is that, look, stars are our long dead ancestors who are looking back at us and smiling or waving their hands. And now 20 years later, now that I'm on a path to getting a PhD in astronomy, I think that there is at least some truth to that statement, even though if it is for the wrong reasons. So today I will try to talk about how stars are linked to our own origins. In the process, we'll look at how our own sun will evolve in the future and how these explosions happen and how they create the elements that we are made of today. So if you look around yourself, the oxygen that you breathe, the calcium in your bones, the iron in your red blood cells, the gold and silver used in your jewelry, pretty much everything around you came from stars. The Big Bang only gave us two elements, hydrogen and helium, and some trace amount of lithium, but everything else after that, this entire block, pretty much came either directly or indirectly from stars. And in this talk, I will specifically focus on exploding stars. Before we get into any subject, it's generally a good idea to look at the scales that we're dealing with. For example, how big are things? How massive are they? How hot are they? The sun, which is the nearest star to planet Earth, weighs a whopping 2 times 10 to the 30 kilograms. That's a huge number. To put that in perspective, it's like the number 2 followed by 30 zeros after it. And in fact, 99.8% of all mass in the solar system is contained in the sun. So all the planets, all the asteroids, comets, everything else combined only makes 0.2% of all the mass. So the sun is by far the most dominant object in the solar system. And it's also pretty big. It's 860,000 miles across. For comparison, this is how big the Earth is. You see that? That's how big the Earth is compared to the sun. So the Earth is really gigantic, and it's also pretty hot. On the surface, the temperature is 5,500 degrees Celsius. For comparison, water boils in the kitchen at around 100 degrees Celsius. So it's way hotter than the boiling point of water. And in fact, the core is even more terrifyingly hot at 15 million degrees Celsius. But the sun is a rather unremarkable star in the vast cosmic arena. There is a huge diversity in the kind of stars that you can find. And the best way to study the star's diversity is through something called the Hertzsprung-Russell diagram, or in simpler terms, the luminosity versus temperature diagram. So in this chart, on the horizontal x-axis, what we have is the temperature, the surface temperature of the star. And because astronomers are certified weirdos, they have the axis flipped. So the temperature increases as you go to the left rather than increasing as you go to the right. So temperature on the horizontal axis and luminosity on the vertical axis. And luminosity basically is how much energy does the star produce every second. You can think of it as a measure for the brightness of the star, the intrinsic brightness of the star. So if you go out and measure these two properties, the temperature and the luminosity, for a bunch of different stars, you find that they all don't randomly scatter along this plot. In fact, most of them lie neatly along this narrow band in the center that we call the main sequence. And then there are some stars that are giants. Some of them are supergiants, really big stars that can have a radius of nearly 1,000 times bigger than our own sun. And then in the bottom left corner, you find some other exotic objects known as white dwarfs, which are hot in temperature, but they are so small that they don't have a lot of luminosity. They're not very bright. And our own sun lies somewhere around in the middle here. So it's not a very cool star, but it's not a very hot star either. It's just an average star. And the property that distinguishes these stars from each other on the main sequence is mass. The mass of a star is the most fundamental property of a star. It determines everything else about it. How hot the star is going to be, how luminous is it going to be, how big is the star going to be, how long is it going to live. Everything else is determined by mass. Now you may be wondering, well, that's all good, but a star is a giant ball of gas, but what holds it together? You know that the star is really massive. It has, as I said, 2 times 10 to the 30 kilograms of mass inside it, the sun. So what keeps it together? Why doesn't all that mass just collapse in itself? Now, because the sun is a giant ball of gas, gas has a lot of pressure. And the hotter the gas, the more pressure it will have. So the sun, in sun, what's happening is that the inward gravity trying to push it down, is exactly counteracted by the outward pressure that is provided by the hot gas. In physics, this is called known as the hydrostatic equilibrium. But it is, at a fundamental level, is just a force balance, that the inward gravity is balanced by the outward pressure. In a star, that outward pressure and the heat necessary to maintain that pressure comes from fusion. And at a basic level, fusion is just combining 2 lighter elements to smaller nuclei to give a larger nucleus, and in the process, some energy is released. So fusion is what provides the energy and keeps the star going. And in the sun, and in fact all main sequence stars, the main process that's going on is that hydrogen is being turned into helium. And 4 hydrogen nuclei, the net reaction is that 4 hydrogen nuclei come together to make 1 helium nucleus and release some energy. But why does this transformation release some energy? To answer that, you have to look at the relative masses of these objects. The 4 hydrogen atoms that join together to form helium are actually slightly heavier than the product helium. And this tiny mass difference accounts for the energy released. Using that famous equation that of Albert Einstein's that you find these days more on t-shirts and in rap songs than in textbooks, E equals mc squared. So the mass difference between these two, the reactants and the product, is converted entirely into pure energy. And it is this energy that keeps the star in balance, provides the outward pressure to contract the inward gravity. And all stars on the main sequence, all of these stars are in fact converting hydrogen into helium. So now let's take a look at specifically at the sun. What is the sun doing and what will happen to it in the future? So right now, the sun has a core where the temperature is high enough, it's 15 million degrees Celsius, the right temperature required for hydrogen to fuse into helium. In the core, hydrogen is being converted into helium. And outside is just an envelope of hydrogen, which is not fusing. It is hot for sure, but it's not currently fusing. And this fusion here provides all the outward pressure that is necessary to counteract the gravity. Therefore, the sun is a ball that does not, you don't see the sun change in size from day to day. It has been pretty much the same size for the last few billion years. But let's fast forward 5 billion years into the future and see what happens. So as hydrogen is being converted into helium in the core has more and more helium left over. And helium needs a lot higher temperature to fuse into heavier elements. Now hydrogen fuses at 15 million Celsius, but helium requires even much larger temperature to fuse. So this helium at the moment just stays in there doing nothing. And temporarily that means the outward pressure is diminishing. And that allows this core to contract because there is no more pressure that would keep the star in balance. So temporarily at least, the core collapses or contracts slowly. And you might have seen this from your experience that when you try to compress gas into a smaller volume, it heats up. And that's exactly what happens with this helium core. It heats up as it contracts. And in fact, it heats up to a point where the temperature reaches this magic number of 100 million degrees Celsius. And now helium can start fusing. So now helium fuses, makes other elements like carbon and oxygen, and that reproduces the pressure that is required to stabilize the star again. So now the star has again reached another stable position where it can start fusing helium for a while. So at this point, what we have is that we are fusing helium in the center, followed by a shell of hydrogen, because all the hydrogen that was displaced by the presence of helium is getting so hot outside that it will also start fusing. So you have helium burning in the middle and then hydrogen burning right outside it. And because now two different fusion processes are happening, so much energy is released that it actually causes the outer envelope to expand. It heats up the gas outside so much, and heated gases expand generally, so that causes the hydrogen envelope to expand, resulting in a red giant. So that's the process how a sun-like star can become a red giant. You start fusing helium in the middle, and then you have a shell of hydrogen burning, and combined, they produce so much energy that they actually cause the outer envelopes to expand. But well, the sun doesn't have an unlimited amount of helium inside it. Helium will eventually run out. And because helium was being converted into carbon and oxygen stays in the middle. Helium now is on the outer ring, and even outer ring contains the hydrogen. So now we have this differentiated structure in the star. But the sun will never get hot enough to start fusing carbon and oxygen. There is simply just not enough mass in the sun to contract the core so much that it can fuse carbon and oxygen into heavier elements like sodium or magnesium or sulfur and so on. So this carbon and oxygen core remains unreactive. It won't burn anymore. It will just stay there. And these outer layers, slowly but surely, will be ejected outwards in a process known as a planetary nebula. So the inner core remains inert, it does nothing, it just stays there as it is, and the outer envelopes slowly are shed out in something called a planetary nebula. And these planetary nebula are beautiful. So here are two examples of these. These are actual real pictures. In the middle is that carbon-oxygen core that is not reacting anymore, not fusing anymore. And outside, these stellar layers have been gently ejected. It's not an explosion, it's just a gentle ejection of wind. And I hope that when sun dies in the next 5 billion years, I hope that our own sun's nebula looks as pretty as this, or maybe even more, for some other aliens to enjoy sometime in the future. So that's planetary nebula, that's how the sun will die, leaving behind this carbon-oxygen core, which we call a white dwarf. So a white dwarf is left behind, that is this carbon-oxygen core, we just call it a white dwarf. And these white dwarfs occupy this space. So they are hot in general, and because they're fairly small, they're not very bright. They don't appear very bright. They're typically the size of Earth, comparable to the size of Earth. That means they're 100 times smaller than the sun, but they're really dense. They can contain a mass up to a solar mass on average. So an entire sun's mass crunched down into a space taken no more than the space taken by Earth. So that's a super dense object, and it's a very exotic object. And you may be wondering that, hey, well, there's no fusion taking place, then what keeps it in its place? What holds it together? Why doesn't it just collapse? Well, there's something called electron degeneracy pressure. It is this weird quantum mechanical effect that happens when electrons are pushed very close to each other. Electrons, turns out, unlike some human beings, actually like the idea of physical distancing. So if you try to put electrons very close to each other, they would quantum mechanically produce an extra pressure to make sure that no two electrons occupy the same quantum state. So there's this weird electronic pressure, degeneracy pressure, that keeps white dwarf in its place. And white dwarfs can sometimes be found in binary orbits with other normal stars. And what that means is that a white dwarf and a normal star are dancing around each other, they're orbiting each other. And occasionally, some mass can transfer from this normal star onto the white dwarf. And turns out, because of these quantum mechanical properties of white dwarf, it has an upper limit on how massive it can get. And it is, as the mass goes on to white dwarf, the maximum mass the white dwarf can have is 1.4 times the sun's mass. As soon as this magic number is reached, uncontrolled nuclear reactions happen on white dwarf, and the white dwarf goes kaboom. It's literally a giant thermonuclear weapon in space waiting to detonate as soon as the mass exceeds 1.4 solar masses. So appropriately, this thing is called a thermonuclear explosion of a white dwarf, exactly like how nuclear weapons go off. And in astronomy, at least, we call it a type 1A supernova. There are so many different types of supernova that you can get that it's actually a good practice to have classifications of them. So this is one way you can get a supernova explosion, the explosion of a white dwarf. But then there are other ways, and the main other way that I want to talk about is when high mass stars evolve out of the main sequence. So white dwarfs, you get white dwarfs through stars that are low mass end, like Sun and other lower mass stars. High mass stars are somewhat different. So what happens is that they have the similar process to begin with, like the Sun. They have this structure, the shell structure, where you have hydrogen, helium, carbon, neon, oxygen, and heavier elements sink deeper into the core of the star. And they're all causing a fusion. So hydrogen is fusing into helium, helium is fusing into carbon, carbon is fusing into neon, and so on. And this can happen in a high mass star because the temperature inside the core of a high mass star is so much that it doesn't just stop at carbon and oxygen, as in the case of the Sun, but it can go all the way down until it reaches iron. And iron is a death sentence for a star. To understand why, let's take a look at this plot. So in this graph, what we're plotting is, on the x-axis, the horizontal axis, we have the mass number of the atom. That is, how many protons and neutrons make up the nucleus. And on the y-axis, we have something called the binding energy per nucleon. You can think of it as a measure of how stable the nucleus is. So this graph actually peaks around iron, which tells us that iron is the most stable nucleus in all of chemistry. All the elements that are to the left of iron will tend to fuse. So if you give them enough heat, you give them right density, they can fuse to make heavier and heavier elements that are more stable than the other one. So hydrogen can fuse to make helium, helium being more stable than hydrogen. Helium can fuse to make carbon and oxygen being more stable than helium, and so on, until you reach iron. And elements that are on the right side of iron tend to undergo fission. So these are gigantic atoms, and by gigantic I mean on nuclear, in terms of nuclear scales. They have so many protons and neutrons that they are naturally unstable, and they like to break apart and form smaller elements that are a little more stable. So for example, uranium in nuclear reactors and nuclear weapons undergoes fission to form other products that are smaller in size. So iron has this special position here, which at the peak. And the problem with fusing iron is that if you try to fuse iron to make heavier elements, it actually doesn't produce any energy from fusion. Instead, it actually takes energy from its surroundings. And that is a problem for a star. So rather than producing energy in the fusion, it actually takes energy out of the system. So what happens, as soon as you form an iron core in the middle, that pressure support that holds the star together goes off, because there's no more iron cannot fuse. And the fact that iron is not fusing means that pressure suddenly disappears. Now gravity is winning here. The gravity will take over instantaneously, and it will start collapsing the entire star. First collapses the center, the core itself. The core falls down into a very tiny point, to a tiny size, the size of a city block, like around 10 miles across. And that object is another exotic object known as a neutron star. It is made primarily of neutrons. It's incredibly dense, and it's very rigid. It's very solid stuff. It's very hard to compress a neutron star. So all the material that was falling behind on it encounters this extremely rigid body and bounces right back up. And it is this bounce back of material off of a neutron star that drives the explosion in a core collapse supernova. To be fair, it's really the neutrinos that drive it. Neutrinos come from during the production of neutron star itself. They're a byproduct of formation of neutron star. And so many of these neutrinos are formed and they're all trying to escape the star, that they actually give all this material an extra push. They give the oomph to this explosion. And it's a double whammy, really. All the material is bouncing back, and on top of that, all these neutrinos that are trying to escape also ram into this material, making the explosion go even faster. So the explosion itself can be so fast that the ejected material can go up to speeds of like a few % of speed of light. That's incredibly fast. A lot of energy is being released during this explosion. And this explosion on the screen right now may look super terrifying and all, but this is just an artist's rendition. We don't really see this happen in real time. What astronomers really see is this. It's a flash of light that comes near a galaxy. It brightens over the time of 2 weeks, and then slowly fades back over the next few months or so. So that's what it actually looks like. Not super impressive as an explosion, but this point of light can actually give us a lot of information about the supernova. And in fact, most supernova that we know of today, we're approaching something like 10,000 known supernovae by now. They're all extragalactic. That means they are discovered in galaxies other than the Milky Way. In our own galaxy, the rate at which supernova explosions happen is something like once every 50 years or so. So that's a fairly slow rate. So every 50 years or so, there should be an explosion going on in our own galaxy. But actually, we see far few explosions than this rate. And the reason for that is that our own galaxy has a lot of dust. All the stars that you see outside, if you go outside tonight and you look up, all the stars that you see are in a very tiny fraction of the sun. It's called the solar neighborhood. They're all very close to the sun. And because the galaxy is so big, the odds that an explosion will happen every 50 years in our own solar neighborhood are absolutely minuscule. So it's very rare that we see a supernova explosion go off in our own galaxy. In fact, the last naked eye explosion that we saw in our own galaxy was in the year 1604 AD, which was known as Kepler's supernova, and it's this image shown on the right. This is what the supernova looks like today. This is the remaining gases that have been expanding ever since the explosion. So it's been more than 400 years since the last supernova explosion was seen in our own galaxy. Then naturally, you may be wondering, well, when is the next one going to happen? To be fair, we don't really know exactly when the next will happen, but we have some best guesses. And Betelgeuse is one of our best guesses for being the next naked eye supernova explosion in our own galaxy. So Betelgeuse is a red supergiant star that is in the constellation Orion. You can see this constellation in winter months. It's not visible right now, but starting October or November, you will be able to see this. And this star is so big that its diameter is bigger than Jupiter's orbit around the sun. It's really, really big. And it is expected that this star will go kaboom in something like the next 10,000 to 1,000,000 years. And I personally really hope that this explosion happens in our own lifetime, because when it goes off, it will be so bright that it will seem like the Earth has 2 full moons in the night sky. But well, the universe rarely, cares about what I think. So, well, it'll go off whenever it has to go off. But whenever it goes off, that will be a sight to behold. But for now, we can try and understand what astronomers really do with so many of these supernova explosions that are extragalactic in nature. So one of the strategies that we use to detect these supernova explosions is that we picture the whole night sky every few days. So say we took the pictures of entire sky today, then 2 days later we revisit, we take pictures again, and then we compare the new pictures to the old pictures. So here you have a new picture, and here's a dot of light that is seen near a galaxy, but in some old reference image, that dot is missing. And when you subtract that, you can isolate the light of that supernova. At this stage, we just call it a supernova candidate because we're not yet sure that it is a supernova. We have to run further tests on it. But this is the way we isolate most of supernova explosions. So we can subtract a reference image and a new image and to get the point of light. Currently, the leading facility that detects the supernova is the Zwicky Transient Facility, and it detects about 1 to 2 supernova every night. So that's a lot of supernova. There's a huge field. There's so many objects being detected. And in fact, in the future, in the next 5 to 6 years, this number might go up to 10 to 20 supernova per night. And in fact, some estimates say that there is a supernova going off somewhere in the universe every second. So there goes one, another, so on. But because the universe is so huge, we can only see and detect a very tiny number of them. Right now, we're only averaging 1 to 2 a night, but in the future, we will very likely average in tens. So we have a lot of data. And once we have identified a candidate, a supernova candidate, what we can do is repeatedly take pictures of that part of the sky to see how the brightness of that supernova evolves over time. So in this picture over here, I've encircled a supernova candidate. All other points of light that you see here are stars in our own galaxy that just happen to be along the line of sight of this galaxy. So if you go along, you see that this point of light increases in brightness. It's getting brighter and brighter, gets to a maximum point, and then it slowly decreases in brightness and fades away over time. And if you look at the dates, it takes about 2 weeks on average to get to maximum brightness, and then about 2 to 3 months for it to fade. So it rises fairly rapidly and fades away very slowly. So what you can do is plot the brightness of the supernova against time. And what we get is something like this. Now, as I said, there are many different types of supernovae explosions, and each type has a very different behavior in a distinct pattern in its brightness profile. So you see that over time, it takes about 20 something days, between 10 and 20 days for the brightness to reach a maximum. And then the brightness decreases over time over the next 2 to 3 months, and the supernova fades. But there is even better way to actually study supernova explosions. And that is to pass the light of the supernova through a prism. So if you pass white light through a prism, what you get is a spectrum of colors. The prism divides that white light into its constituent colors of different wavelengths. So the red light over here has the longest wavelength. The blues and the purples have shorter wavelengths. So what we can do is we can pass light coming off from a supernova through a prism like this and study how the brightness varies as a function of the wavelength. So am I getting more light for red wavelengths compared to the green light, and so on. And the advantage of doing this is that the elements in the supernova explosion tend to absorb light at a very specific wavelength. So for example, let's take a look at this chart. On the x-axis, on the horizontal axis, we have wavelength, which is effectively the color. So the longer wavelengths are redder in color, shorter wavelengths are bluer in color. And we're measuring how much energy do we receive in our telescope at that specific wavelength. So for example, silicon tends to favorably absorb light of these two wavelengths. And helium would absorb light at a different wavelength, and oxygen at different wavelengths, and so on. So by studying the pattern of this absorption and emission, we can actually tell what elements are present in their supernova explosion. And different type of explosions have different elements in them. For example, type 1 supernova, which specifically type 1a, the explosion that was the thermonuclear explosion of a white dwarf, does not have any hydrogen in it. So it has silicon, helium, oxygen, magnesium, and a bunch of other elements, but it does not have any hydrogen in it. Type 2 explosion, on the other hand, the one which comes from massive stars and their cores collapsing, has a lot of hydrogen, and it is dominated by this profile called the H-alpha, the hydrogen alpha. So by looking at differences in the absorption lines, we can tell exactly what kind of explosion that is and what elements are contained in that explosion. And it is partly because of this evidence that we are able to tell that, hey, all these elements actually were synthesized in a supernova explosion or in a star. So the spectrum of stars is an incredibly useful tool in studying these explosions. So we have seen so far that before explosion, even before explosion, stars can form up until iron inside them. But during the explosion itself, a flurry of other elements can be formed. And the reason is that, as I said, elements beyond iron require energy to fuse. They don't produce their own energy when they fuse, they actually take energy out of the system to fuse. Well, when an explosion happens, it provides all that extra energy. So all that energy from the explosion itself can drive fusion of all these elements, most of which are not very stable, and then they decay back. They in fact undergo fission back into more stable objects. So eventually what we get is that we get a flurry of these other heavier mass elements as a product of the explosion itself. So there we go. We have all the elements from fusion and fission, and more or less our periodic table is complete from stars alone. And then these explosions scatter these gases everywhere. These gases can go far away into other stars and other stellar neighborhoods. And over many cycles, these enriched gases with all these heavy elements can mix with even bigger gas clouds, like this one. This is the famous Orion Nebula, which is also in the Orion constellation. And this is a really big gas cloud. And part of this gas cloud at some time in the future, for reasons that we don't really clearly understand at the moment, might begin to collapse. And it may form lumps and smaller lumps. And some of those lumps will then go on to become their own stars, new stars. And the disks around them, the dirt in them, the gas and the gas and the particles in them will go on and form planets around them. A similar process like this 5 billion years ago formed the planet Earth. And somehow on this planet, life emerged. We don't exactly know how. We don't have a theory of life. We don't entirely understand how life came to be, but it did. And life produced a host of organisms, but it also produced thinking human beings who can actually look back at these stars and wonder, well, where did we come from? What are these objects? Why are they there? So my hope is that the next time you go outside and look to the sky, you'll think about the spectacular processes taking place far away in the universe. In real time, processes are taking place that will lead to birth of other stars, other planets, and maybe other life forms, and some of whom may eventually develop thinking ability and may ponder the same questions about our own origins. So with that, I'll rest here. Thank you for your time, and I'll be happy to take a few questions now.